afternoon, ladies and gentlemen. It's my pleasure to welcome you to this special interest talk to be presented by Professor Papken of Hovsepian. I outlined this morning a little bit in the opening ceremony about these interest talks, a new feature at ICMCTF, and you will see if you follow us throughout this week what we mean with these talks. We have a diverse approach, multiple different talks and different topics. And one aspect of these special interest talks is to highlight and recognize colleagues that have done pioneering work in fields of interest to ICMCTF, who have done outstanding service to ICMCTF and have an impact on our research community. And this holds absolutely true for Papken of Hovsepian. Papken is truly a pioneer in physical vapor deposition. He has more than 30 years experience in this field. He has done significant work on cathodic light evaporation, on magnetron sputtering. A special interest of his work was always the development of high-fried deposition processes, combining the different methods. And I would say, in a personal estimation, his impact on the work on the pulse deposition processes in the last 15 years, together with Harry, of course, and other colleagues, but his impact is significant, and the pulse deposition would also not have reached the level it has today. Papken is professor and head of the Thin Films Research Center at Materials and Science Engineering Research Institute in Sheffield Hallam University in England. And when he came in 1997 to this institution, he was very soon a fundament and solid rock on which other colleagues, and especially here in our field, Peter Münz, could build on. And together, these two pioneers have published seminal papers on nanoscale multilayer thin films and superlattice thin films, on transition metal nitrides and other material combinations. And if you look on these papers, you will find that already 20 years ago, these colleagues, and especially Papken, anticipated a lot of that what we talk today about interface engineering in multilayer materials. A very impressive part of Papken's work was always the intention to translate US research work into practical applications, into industrial deposition processes and final applications. And in this regard, he is a highly wanted and often searched for cooperator with industry and academia, so he is building a bridge between the two worlds, and this is also very important to our community. Here at the conference, Papken has contributed since decades on highest level and outstanding service to all of us. And those of you who are new in the conference, you might look into the old program books 20 years ago or so. You will find him as a session chair in many functions, and his advice on all these fields we have developed at ICMCTF so far was really important to us. And it's my great pleasure now to introduce and let Papken have the word, and he will give a review of some examples what he did in the past decades. Outstanding work, and I just wish you fun, enjoy this talk, and thanks to Papken for a really outstanding contribution to our community and conference.
Thank you, Michael, for this introduction. I will just use the word fun. You use it. I am intending to have fun this afternoon. I'm in the field 40 years, not 30 years. I was a student when I started with PVD for some reason, and it stayed with me all my life. So it is true that I always worked in the field of applied research, and I'm not very ashamed of that. I like seeing results being implemented in industry. And what I will do, I will try in the next 40 minutes to keep you, of course, entertained, but also to show you the pain we went through develop some of these materials, which were postulated a long time ago as super materials, and the results which we have achieved in this field. So the title already says that these are coatings which will work in demanding environments, and the environments which I will touch, they include lead corrosion, room and high temperature oxidation and corrosion resistance, interaction with workpiece materials during cutting, and interaction with the human body. So it's a very wide range of environments, and one has to have a specific approach. And the approach we followed during this research for all these years was always the following. We would start first with careful investigation of the application itself. So it's paramount, it's very important that you understand the application, and then you start designing and using different approaches how to handle this application. Now, super lattices are layered materials. Basically, two materials can be layered when they're in the nanometer range. This would be already in the definition of super lattice. And they were discovered around 1925 in an attempt to develop new type of X-ray mirrors. And their first industrial application was demonstrated by Sumitomo as coating on cutting tools, and Nanoscale Multilayer, as we call it, or super lattices, were aluminum and titanium nitride at that time. Around 1970, I think James Kohler was the first person who introduced the theory behind the super lattices. And the theory was that if you marry two materials with different elastic constants, then you automatically create a barrier for the dislocation motion, and the energy they need to cross this barrier is proportional to the difference between the elastic modules. So it was a very, really interesting concept because this gave in our hands the tool to manufacture man-made new materials. And it was demonstrated that a huge hardness enhancement can be achieved in a specific bi-layer period range. Now this was the attraction for many years, and the goal was always to get hardness and harder materials. The super hardness as a term was introduced, and everything which is 140 gigapascal was named super hard. Now the theories which explain this, and there was huge amount of research which I'm not going to touch deeply, but I selected just 4 very comprehensive theories which explain the hardening effect, starting with the hole patch, which you all know, which was developed for bulk materials, but it can somehow apply in condensed materials as well, on vapor phase. Supermodules effect was the next attempt to explain the hardening by claiming that you can have sometimes between 100%, 150% to 500% increase of the modules, elastic modules, and therefore you can get hardness enhancement. The coherency strength effect was based on the fact that if you have two materials with different crystallographic structures, then you automatically create a barrier for dislocation motion, and therefore hardening effect. But the theory which I really, all these years, liked most was the one which was proposed by Schuller Barnett, and they were saying that depending on the thickness of the individual layers, you can have three cases: very thin layers where you cannot develop dislocations at all, so therefore your hardness is low; very thick layers where the material just behaves like an ordinary multilayer material, and the specific range of bilayer thicknesses where the dislocations will be generated in the softer material, but they will not be able to jump in the harder material, and therefore you get hardening effect. Now, lots of papers have been published. The most popular, at least in our group at that time, was coming from ring chopping. Huge hardness enhancement, I don't know, here in this graph, the sky is the limit. And I was always puzzled by that, because one of the co-workers in this group was a colleague of mine, actually, from Bulgaria. And I have had long discussions how they have measured this. But that is what was published. The Japanese guys were a little bit more modest. They said that, of course, there is a hardness enhancement in a specific bilayer thickness range, but it is in the range of 40-45 kilopascal. We found similar, in our research, similar hardness enhancement. But still, it is important to know that in a specific bilayer thickness range, you really get hardness enhancement. So this was not a false, I would say, claim. It was just the fact that when you go in this range of hardnesses, it is so difficult to be accurate in the measurement. We all know that this is a really dangerous area. This is how a superlattice looks like, multi-layers. Compared to the monolithic uniform coating, these are much denser structures. You don't have the columnar growth, the voids. And to deposit such materials, you need a specialized equipment. This is a picture of a Hauser machine, which we have in our center. It has 4 sources, plasma sources. And if you furnish these 2 sources with one material and these 2 sources with another material, and simply by sequential exposure of the surfaces by rotation to the fluxes coming from these 2 pairs of magnetrons, you end up with the layer structure. In 2000, we were basically forced by industry to demonstrate that we can deposit with high precision these fine multilayer structures on 3-dimensional components. And this shows you an ASIM cross-section of a scalpel blade coated with A coating, and in TM you can clearly see, I hope you can see them, I don't know, the light could be very different for you, but you can see the layer structure. So it was clear that we can put these coatings on a cutting tool, on a turbine blade, or whatever 3-dimensional component with very high accuracy. What we also liked was the behavior of these layered materials in tribological applications. So this is the friction force in monolithical materials, in monolithically grown materials. You can easily open tensile cracks at the column boundaries. You can release huge particles which act as third body in the sliding contact and produce these very groovy wear tracks. Whereas nanoscale multilayers tend to deflect cracks, they produce very fine wear debris, and therefore you end up with a very fine surfaces. What is very important to be understood for this type of materials is that because of their very high hardness, they're also highly stressed. So therefore, a good nanoscale multilayer coating or superlattice coating is a coating which is very strongly bonded to the substrate. This is a published work which we did in our lab in 1998, I believe, where we showed that the lifetime of an end mill is proportional to the adhesion of the coating deposit of this end mill. And we use different approaches, different pre-treatment steps, different etchings, as we call them. Here's the argon etching, and here's an optimized chromium etching using arc discharge. You can clearly see that this is a very important parameter. And this is where actually high films helped us immensely, because high films is discharge which generates metal ions. This is one of the waveforms from the early first generation power supplies. So you can see we can go to very high voltages, and using the pulsed approach, we can really go to very, very high power densities and therefore generate plasma which is highly ionized, metal plasma which is highly ionized. And after the first papers on high films showing that perhaps this technology is capable to produce ions, we did some measurements, we found these ions, and I think in 2001 we patented the metal ion etching using high films. Now, you can clearly see the benefits of using metal ion etching by high films. If this is your substrate, this is your coating, and if you analyze the chemical composition of the interface after being bombarded with chromium ions, you find that you can implant this species deep into the substrate. And this has huge implications on the structure of the crystallographic structure of the interface. This is an interface which is prepared by argon etching. It's almost amorphized, it is highly disordered. And this is the structure of the interface after high films etching. This type of crystallographically perfect interfaces produced by implantation trigger afterwards during the coating growth stage local epitaxial growth. The difference what we saw, because we were practicing metal ion etching with arc for many years, but the difference which we saw with high films was that we can have local epitaxial growth on very, very large areas of the substrate. Also taking into account that arc generates droplets, and if you take the time and calculate how much of the surface is actually covered by droplets when you use evaporation for pre-treatment. I will give you just one example. For titanium, it's approximately 19%. These droplets are not metallurgically bonded to the substrate. They arrive here, they solidify, there's no bonding. So 19% of your surface is out from contributing to the adhesion strand. So therefore, there is no wonder that the adhesion of high films pre-treated coatings and surfaces and coatings is higher than the one produced by ARC. In both cases, we have metal ion etching. In both cases, we have local taxel weld, but here we have low adhesion than using high pins. So a big difference can be also seen in the coating structure. This is a chromite and aluminum nitride nanoscale multilayer deposited by ambulance microsputtering, arc evaporation, and hybrid. With technology which provides very low energy on the arrival species on the substrate, you often see these voids and very wavy layers. Arc is perfect, it gives you very good interfaces, but arc will also generate a droplet. It's a droplet inside of the coating, and you can see the defect which grows, and you can see the compressive stress in the coating, which is able to close these defects after 80 nanometers of growth. With high prims, your layers are really with sharp interfaces. They're not wavy. You don't have the defects in the arc. So basically, this structure is winning from this point of view compared to state-of-the-art technologies. Now, if you go further and investigate the coating density, this is just an example. Nobody is depositing in the real life micron sputtered coating with zero bias. I used this picture just to show the danger of having open structures and to contrast it to what we see with high prims. This is a plan view. You make a cross section like this and observe from the top. These are the columns, and these are the column boundaries. So this is a 3-point meeting point between 3 columns, and you can see clearly the atomic place from this column continuing in the next column, and there is no mismatch, no voids or imperfections. So this is a really bulk material type of testing. I remember we had long years of cooperation with the Japanese professor who would come to Sheffield and say, Papken, show us the symbol of high pins. And we couldn't understand what this professor wants. But with time, when we saw this picture, perhaps this is a symbol of high pins. It's very high density of the material. So now you have high pins, which helps you to produce very high adhesion and produce very dense coatings. And with being able to combine different materials, you can develop really various types of coatings to address particular conditions. And we have developed these types of coatings, which I will describe very quickly in the next half an hour. And we used to call it Sheffield Hallam University Nanoscale Multilayer coating family. So I will speak about 6 strategies which we followed, depending on the application. And the first strategy was to combine elements producing dense oxide scales with rare earth elements like yttrium, for example. And the application foreseen was protection against environmental attack at high temperature, basically high temperature oxidation resistant type of coatings. Now, we had the yttrium concept a long time ago, sterilizing that aluminum nitride with yttrium for dry high-speed milling. But yttrium at that time was introduced in the coating. With this application, we decided to implant yttrium in the interface. And it was not possible to do it by arc because of very huge instabilities if you have it in the target and use arc. But it was very, very easy to do it with high beams. So we have it in the interface with this coating, and we have multi-layers which are based on elements like chromium and aluminum, which produce extremely dense oxide scales. Now, this is how the coating looks like. You have your base layer, the implanted zone, the base layer, and the coating. Very interesting properties. We saw first sign and signature of oxidation after 850 degrees C. Hardness was retained up to 900, very high hardness. Very interesting tribological performance. With temperature, the friction coefficient in high temperature tribological test was reducing. This is very well understood because the oxides which form based on chromium are so-called magnetic type of oxides, so they have low shear stress planes, and therefore the friction coefficient is reducing because you produce these lubricious oxides. The oxidation resistance was also fine. This is how the weight gain of the unprotected material looks like with time, and this is the weight gain when the material is coated. In this case it was gamma titanium aluminide. It was a special project to develop coatings to protect this new generation of future turbine blades, which need to be lightweight and turbines with bigger diameters were needed. So we developed this coating for this application. When you're in this business, it's always important that you preserve the mechanical properties of the base material. PVDs have been always excluded from the arsenal of coatings for turbine applications because of their porosity. If you deposit the coating on a turbine blade, if you're not careful, a crack will develop in the coating and will attack the substrate, and therefore you will lose the fatigue properties of such material. What we found with this coating after fatigue tests, so that is the fatigue resistance of the fatigue strength of the uncoated material. This is when the fatigue deficit when you use ambulance micron sputtering and porous coating, and Hypems was producing only approximately 9% fatigue deficit, which was accepted by the iron industry. So we coated within this project several types of blades. We also translated the coating for automotive components. And the coating was tested by MTU at that time. It was a very special cooperation between ourselves and Hauser, because the final coating which really performed was a Nanoscale multilayer from aluminum nitride chromium nitride with a top coat of aluminum oxide deposited by Hauser. So this combination did pass the test review. Next problem and application was machining of developing of high hardness, low friction vanadium-based nanoscale multilayers, where the strategy was to utilize magnetic phases which form in situ at asperity contact during sliding. You know that in tribological contact you might get up to 800 degrees C in the sliding contact. So therefore, if you have material in your coating which oxidizes, and if the oxide has a magnetic type structure like it is demonstrated here, you can really reduce the friction coefficient by producing this lubricious oxide. With vanadium pentoxide, you also have a benefit of having very low melting point. So this is how the structure looks like. You form a tribal film, 10, 20 nanometers. And if you go and investigate by Raman what is the phase composition of this film, it will be vanadium pentoxide. And incorporation with the oven, I think Paul, I don't see him in the audience, is here. But he produced this nice SEM picture of the wear truck producing high temperature Pinot test, 700 degrees C. You can see this structure which shows you that the ball is actually sliding against molten material, because 700 is above the melting point of the vanadium pan. So this was a very interesting result. If you want to compare and understand why suddenly we were so much attracted by this coating, I just want to show you the wear coefficient in the range of 10 to minus 17. Compare it to the wear coefficient of the DLC and other analytically known coatings with good wear resistance. See the hardness value, see the adhesion, and the friction coefficient, which is not that much different, I must say, from practical point of view, when you compare it to this particular type of DLC. I'm not saying that there are no DLCs which will 0.1. You don't know that. But that was a really interesting coating which combines very high hardness, very good wear resistance, and very low friction coefficient. That was the reason and the attraction behind this strategy. With the next step, we modified this material by bringing carbon in it, and the strategy here was to utilize low shear strength interfaces, which are produced by dynamic segregation of small atomic address elements such as carbon. So if you go to the literature, which was generated before 90s, where people were very active developing theories about superlattices, you will always find the same claim. The interfaces must be sharp. It was just what Barnett published a really nice paper saying, okay, but whatever we do, we have at least 1 nanometer intermixing. And then, knowing about these things, we said perhaps something can be pushed into this area of the coating, right at the interface between the individual layers, and change the whole wear mechanism of this coating. And this type of coating was under our radar because we wanted to machine stick alloys, which produce huge build-up layers. And here's what happens. If you add carbon to the straight adenine nitride or vanadium nitride, it does segregate right at the interfaces. You see this. This is a carbon-free coating, and this is a coating which has carbon. And this is carbon. We have published this, we have studied this very carefully, so I have no time to show you all these results. But carbon is segregating at the interfaces. In machining of aluminum alloys, we saw that we can outperform the carbon-free version of the vanadium superlattice coating. We were much better than DLC. And this is just the schematic. That is the carbon-free version, the individual layers. You always form a tribal film on top. It does react with your aluminum workpiece material, produces huge build-up layer, then it will shear away this interface here, and big chunk of material, of coating material will be lost. When carbon is segregated in the interfaces, you are in a layer-by-layer wear mechanism, and this layer-by-layer wear mechanism is on nanoscale. So therefore, with this approach, you don't actually prevent the metallurgical reaction, because you cannot cheat nature. But you can produce a material which has a special topological behavior. And applications are clear. We were in a project with Fiat at that time. They wanted to machine lots of aluminum cutting, drilling, tapping for automotive components. Airbus wanted to machine airplane wings, and this is basically machining of aluminum 7010. Huge blocks of aluminum will be reduced to a very, very fine structure like this, lightweight. But we were also very good in machining titanium alloys. And this is a case where we show that we can enhance we can improve the number of we can improve the lifetime of our tool by almost factor of 3 by machining 3 times more components for medical implants. So we cannot explain this. We cannot explain these results by saying, okay, our coating is inert. Because if it is inert to aluminum, it definitely reacts with titanium. This coating has a different wear mechanism. The fourth strategy and the fifth strategy, which I will explain, around metal-doped carbon films. And here we wanted to use the high ion irradiation to achieve a very special growth, which is based on self-organized nanostructures and dynamic phase separation. So metal-doped carbon films have been introduced by Dennis Steer. They were patented by Dennis Steer. So what we wanted is to find ways eventually to get new properties, a new type of performance based on the tools which we have in our hands, and this was the ion irradiation, just using different bias voltages. Now this is a coating deposited at low bias voltage. It is amorphous. It is chromium-doped carbon film. You go to a little bit higher bias voltage, you further reduce the friction coefficient. This is a typical friction coefficient range. But you also start finding in high-resolution TM very interesting onion types of structures. I think Lin Chopping Group has published lots of papers on explaining why this curvature is happening. And this was clear somehow to this point. And Raman shows you that with increasing bias voltage, you start somehow changing from the typical graphite type of Raman spectra to more carbide type of Raman spectra. And what was the most intriguing thing, that when we moved to the high bias voltage range, we suddenly found a material which is perfectly layered, and the bilayer thickness was certainly not corresponding to the rotation speed and the power which we use on the magnetons, because it was abnormally large. It was 20 to 30 nanometers. We found these very special structures, phonium-like structures, and with time, we did lots of analysis to show that this is actually a pure, almost pure carbon. There were 95% carbon. And you can clearly see that it is ion bombardment related growth, because if you increase the bias voltage from 350 to 450, you get different bilayer thickness. And you can destroy this growth if you go to very high bias voltages. So that was a very interesting growth based on carbon segregation, and you can actually show very clearly this based on the irradiation effects, because this sample was produced in one deposition run. Half an hour the coating was deposited 75. In the next half an hour 350. You reverse it to 75 and you reverse this structure. It is very reproducible. You can see all the signatures of the ion bombardment, low ion bombardment. You can see the tops of the columns, very rough surface. High ion bombardment, this is the end of the cycle, very smooth surface because of the resputtering. And you can clearly see that you can just switch from amorphous to this layer structure absolutely accurately. Application was coatings on, I will call them fine blades. This is just the cutting edge. This is a cross section, very high aspect ratio, very sharp blades, which reduce the cutting forces and the lifetime of the blade. Strategy 5, again, method of carbon films, where we wanted to utilize the thermochemical reactions to achieve in situ formation of nucleus phases in conditions of boundary lubrication. Application was low friction, high resistant biological coatings, which need to operate at boundary lubricated conditions, but at elevated temperatures. It's a coating where we doped carbon with molybdenum tungsten. I think we patented this solution. This is the typical structure of such coating. And what happens is that these two elements react with the sulfur with the oil, and they produce low shear strength magnetic phases like MOS2 and WS2. This coating shows really very low friction coefficient. These are all DLCs. I have put here A, B, C, D because we don't want to reveal exactly who is the supplier and what the DLCs are. But this selection was kindly provided by Hauser, so they had access to all sorts of DLCs. And you can clearly see that this one shows really low friction coefficient. The formation of the MOS2 and WS2 in situ was confirmed by careful analysis of the wear debris after lubricated test at 200 degrees C. And you can see the spectra here of the wear debris. And here, these are the spectra of these two compounds in pure powder condition. We can clearly see that these lines correspond exactly to the powders which we use as control specimens. What was the big difference between the behavior of these coatings and the standard DLCs was their behavior, their friction behavior with time. The standard DLC was having initially very low friction coefficient, but with time it started increasing because at these high temperatures you start getting liquidization and the friction behavior deteriorates, whereas with the molybdenum tungsten doped carbon films, the friction behavior is completely different. It does, the friction coefficient does reduce because you generate more and more and more of this superficial space with time. Applications here. I just wanted to show this also. The test 500 degrees C standard DLC coating is almost evaporated here, and this coating is still intact. So the goal was to produce a coating which withstands high temperatures. And this is the demand from the automotive industry because of the increasing loads, the reduced size of the components. So the load conditions are really very demanding, and you really need this type of coatings if you want to deliver in this application. That is just to show how some components with these coatings look like. And I'm with the last strategy, where we used highly electrochemically stable metals like niobium combined with chromium as a wear-resistant material to produce wear-resistant and electrochemically stable corrosion-resistant coating. So this work was carried out in an attempt to replace hard chrome. So this was the idea. And we have three very interesting applications in this with this coating. Corrosion and wear resistance in wet corrosion application, corrosion and wear resistant coating which protect components in steam turbines, so this is another demanding application, and as a coating for medical implants. It was easy to demonstrate that potential dynamic polarization behavior of this coating is much better than stainless steel. But the real final test to approve this coating was coming from industry, and this is a salt spray test. Whatever you do, they want salt spray results. And this coating can withstand 1,000 hours when it is deposited on stainless steel, and 500 hours when it is deposited on mild steel. The industry standard, the industry requires 300 hours when it is deposited on mild steel. So this coating went to several applications. These are components for textile machines. These are components from automotive industry. This is a ball valve which is used in the petrochemical industry. Deposited coatings from this type improve the lifetime in all these applications. Steam turbines, very aggressive atmosphere. This is just a picture which I just drew from the internet just to show how terrible this surface looks like. But when the coating is deposited on the turbine steel, this is the weight gain. With our coating, this is the weight gain of the P92 substrate without protection. And these are coatings, actually this one is 80 micron thick coating, which is very complicated alloy. And this is a coating produced by BAM, which is an oxide layer, so we were surprised that we can actually outperform this type of materials with our coating. It is very important to see how the high temperature oxidation resistance looks like. So after 2,000 hours, this is the oxygen map. You can see a very thin layer was only oxidized, and if you have some cracks and voids, they will be plugged by this oxide, so basically you protect very effectively the substrate with this coating. So the oxidation resistance was very high, That is a very interesting result. We started looking much closer to what we do to the substrate where we deposit coatings. So it's a high temperature tensile strength test where we saw that actually the tensile strength of our specimen was improved after depositing this coating rather than deteriorated. I put these two pictures which actually coming from this type of test after the observation of the specimens for those who are really interested in the adhesion problem. That is a specimen which has been stretched in this elastic zone of the material. You can see some few cracks because these are huge elongations and you have a ceramic coating, but the coating is still here. It hasn't been delaminated. You go to this area of the test where you form the neck, highly plastically deformed material just before the final break here, and the coating is still here. So that is, we don't do this type of test to test adhesion. We use crash tests and all sorts of barrier events and other tests. But this is a very, very clear message what the metal ion etching can do. We have preserved the fatigue resistance of the material. We have improved the grip behavior of the material. And very interesting results were coming from water droplet erosion tests. So that is the water hammer equation which shows the relation between the water pressure in the droplet and the critical velocity which starts producing first damage on the surface. And this velocity is proportional to the toughness of your material. And in recent years, there was very fine research which demonstrated that the toughness, like the hardness of the material with the nanoscale multilayer structures, in fact is also improving and increasing in the specific bioelectricness range. So these are really very tough materials. And if you don't believe the equations, that is how the surface looks like after such a droplet attack. You have just polishing effect. We have formed a crater here, a dimple, 20 micron deep, and the coating is still intact. And finally, I would like to show you this result. When we applied this coating on implants, we passed all the tests, so the air release was minimized to levels which were undetectable. We didn't have any attack on the cells in the human body. The test on animals, live animals, I hear from the company with whom we work that this type of test costs several millions of dollars. It's not a secret. We work together with Zimmer Biomet, and the coating passed all this tests. This is how a nanoscale multilayer coating is deposited. You can see the flux coming from the different plasma sources surrounding our components. We can see the rotation. You understand that it is a mixed argon-nitrogen atmosphere by the globe. And with this I finish my talk. I have two more slides. One is acknowledgement, and I acknowledge just one person. I acknowledge Bob Determines, who trusted me in 1997 to develop all-nitride nitride. We started together with him. He left us in 2003, so all the coatings of the world's Nanoscale multilayers were developed in our group. But that was the start. I will never forget this opportunity which he gave me. And finally, I also wanted to acknowledge some colleagues with whom I have worked over the years who have helped me with surface analysis, with advice. Some of them are in this room. I can see Lars, I can see Vlad, for example. We have a joint paper with Michael. I can see my colleagues from Hauser, with whom we have worked all these years because of the Hauser machine, and I'm very grateful that I had this chance to enter in such an interesting and demanding area. And the best news for me, at least, as that is not the end, we have now a very interesting task. Perhaps next 5 years we have to find a solution for that. So problems are as many as you might think, and that is a very good area if somebody wants to continue working, to spend his time. Okay, thank you for your attention. I'm sorry if I was a bit longer. But I had to summarize 20 years of work in 40 minutes. So I'm really sorry. Thank you.
Yeah, did I promise too much? He is a perfect teacher. He is a great cooperator, a mentor, a friend to us. And I believe many people have benefited from discussions with Papken. And if you like, if we have time for some questions or comments, we can also discuss with Papken in the afternoon. I guess he will be here in the. Yeah, so very, very impressive talk. Thank you very much, Papken. We recognize this. So, do we have problems, or are you all tired? There's one more talk that I have to promise tonight. Talk by Joe Green in the San Diego room. Another 1.5 hours, so you can next time you can even expand. We have a lot to share with us. Yeah, thank you very much for being here. Thank you, Papken. Thank you.